So Marie-Pierre is an assistant professor at the School of Actuarial Science at Universite Laval in Quebec City, Canada. She's a fellow of the Society of Actuaries, and she holds an educational leadership chair in big data analysis for actuarial science, Intact. Marie-Pierre got her PhD in statistics from McGill, and her research interests are on statistical learning for pricing reserves in general insurance. So I'm very pleased to have you today, and your talk is going to be about reserving for general insurance using long-short networks.
Yes, thank you. So thanks everyone for being online today. So I would first like to thank Mike for and the organizing committee for giving me the opportunity to present today. It's my work with the PhD student Isan Chaoubi, her supervisor Hélène Cossette, and Camille Bess, who is a researcher here at Laval University. So it's a paper that is, it's not up on arXiv, but it should be up very soon if you want to consult it. So all the details are in the paper, and I'll give the main ideas here. It's on micro level reserving for P&C insurance, and we're using an LSTM network. So let me first start with some motivation on why we would want to have micro level reserving. And that starts with what's the general insurance problem of loss reserving. So we start with the claims data. We aggregate the claims data into a loss development triangle. So with respect to accident year on the rows and development years on the column. And then the goal of the reserving exercise is to predict what's on the lower triangle here, so the future periods. But when we do this aggregation step, we lose a lot of information. What happens with the individual claims characteristics? We just don't use them at all in this framework. So with the advent of big data and the statistical models that are really being powerful, this loss of information seems a little bit obsolete, and it's interesting to look at what happens if we consider the reserving at a more granular framework, and if we can take advantage of these individual claims characteristics in the prediction of the reserves. So a typical claim development would look like something like this. So you have the claim occurrence and then reporting, and it's going to be open. So the file will be open with the insurer. And then there will be payments and recoveries. So here I want to stress that some of the payments could be negative. And then the file will be closed. So the claim is settled at some point in time later on. We saw in the real data that we analyzed that a lot of times the file actually reopens later on, and then there are other payments until a final settlement. So the reserving exercise from this point of view is to place yourself at the valuation date and say, according to what happens up to time t star, the valuation date, what will be the payments made on this claim later on. So you can see that there's a challenge because if with file reopenings, if we're on a file that is closed, we cannot assume that the future payments will be actually zero. We are working with discrete time. So why did we do that? Because if you model the exact dates of the payments, there are weekly variations that are not so important for the overall predictions. So we decided to discretize the time, and that's done also by many authors. So you aggregate all the payments that are made in the first development period into one payment, and we used monthly development periods. So here, for example, in the first development period, there was $100 paid, and at the end of the first development period, the claim status was open. So by doing this aggregation by period, you have some development period where the payment is exactly zero because there was no payment in that period. We also have the information that is reported to the insurer at time of file opening, like claimant age, vehicle type, etc. And you could also think about some covariates that are dynamic over time. So for example, the number of reported injury could vary. It could change because some back pain comes in. So the challenge with micro level reserving, well, first, it's not really a challenge, it's more like a requirement. So you need some long tail development because if all the claims are closed after 2 development period, these models are not interesting at all. So we have long tail development. We worked with accident benefits data from Ontario. So these are body injuries, so medical replacement, medical expenses and income replacement benefits, this kind of stuff. So I already talked about the reopenings, that has to be considered, negative payments. We also observed a lot of claims that are open for a long time, and at the end, nothing is paid, so the settlement is at 0. We also had extreme positive payments, so really, really large payments that are made in one lump sum, and the dynamic covariates, as I said. And of course, we have time-censored data, so we need to put ourselves at the time of evaluation. So there's some of the information is not known and cannot be used for estimating the model and building the model. So the objectives of this work is to build a flexible micro-level reserving model in discrete time. We focus on the RBNS claims, and the reason why we do this is because with incurred but not reported claims, they are not reported, so we have absolutely no information on that claim. So it's not really interesting to build a micro-level model based on no information. So we really assume that at least one development period is known on the claim to develop the payment in the futures. It was also very important to me that we have a model that can be built, trained, and validated based on the censored data that is known at valuation date, so that it can be applicable in practice. But we evaluated the performance on fully developed data. So we used historical data and simulated data so that we could evaluate the model performance on the future predicted values. So of course, micro-level reserving models are not new. They date back to the 1990s. Recently, there's a lot of literature on this topic. Tree-based machine learning were applied to granular reserving by a bunch of others. And in the 2020s, we started seeing some reserving models based on neural networks. So we're in this stream of literature, and it's developed in parallel. So we're not going to compare here with the other neural networks paper because it's competing. If there's something in the chat. Oh, okay, sorry. So yeah, so I'm using LSTM networks, which is a type of recurrent neural network. It's really used a lot for sequential information. It's been used for NLP, natural language processing, music generation, handwriting recognition. And the way it works, it's really in this schema here, you can see there's an input that is passed through a special block that has a special architecture and that will output something for the first period. And then the information from the first period flows through the second period. And you can also have another dynamic input at the second period to output something else. And the module here is repeated, so it's the same module period after period. When we saw this, really, we felt that it was applicable to the kind of data that we have in a discrete reserving model because we have new information when the claim developed. So it seems like a good candidate for the type of structure that we have in the data. Okay, so let me start with the model definition and some notation. So we have a data set that contains M reported claims. For claim K, we will denote by SK the set of static information that is known at opening time, like the claimant age, etc. And DKJ will be the set of dynamic information that becomes known at period J on the claim K. We will assume that after N development period, the claim is fully developed. And we use censored data. So at the valuation date, we observed only TK development period for claim K. And it's going to be at most N, but for most claims, it's going to be less than N. So the data set that we used for training and validation and model building is the data set that contains all the static information and the dynamic information up to time evaluation date for all the claims. Everything else that does not fall into this set will be used for testing the model performance at the very end. Some components of the dynamic set are the incremental payment for claim K and period J, which is denoted YKJ. And this indicator IKJ is the indicator that this payment is non-zero. And here it's a non-zero, it's not a greater than zero. So we allow for negatives for the recoveries and we allow for positive, and it's only, this indicator is zero only if there is no payment in the period. So the individual reserve denoted RK would be the sum of the incremental payment for the future development period, TK plus 1, so the next after the valuation date, up to the ultimate period N. So, and here we have the product because whenever Y is 0, I is 0, so this is just 0, and otherwise I is 1. So we have two things to predict for claim K and period J. We'll have the P hat KJ, the predicted probability of non-zero payment. So so we try to predict this variable IKJ. And Y hat KJ is a predicted payment amount given that is non-zero. So the mass at zero is taken care of by this indicator, and the predicted payment, we really work with negatives and positives at the same time, but non-zero. The predicted expected incremental payment in period K period J for claim K is a product of the two. And so we will be able to estimate the reserve by R hat K, which is the sum over all future development period of the predicted expected incremental payments. So here it means the reserving problem amounts to the prediction of the pairs P hat and Y hat for all the future periods. So the main model will be an LSTM neural network. It has two tasks at each period. It has to first do a classification task, which would be the prediction of the P hat, and a regression task would be the prediction of the Y hat. And the input at each period, so I will show you the schema soon, is the claim context, which I will define, and the dynamic information known at period K, which includes J is the actual period, because we repeat the same module in the architecture. So we have to tell the network, so here is the jth period. We have this indicator that the period is observed or not, okay, because in the loss function, we'll only consider the targets for which the observed are actually non-missing. The indicator, and Y star is the centered version of the incremental payment. So in that claim context, you might notice that we dropped something. We dropped the claim status. That was something we had to discuss because it was not an easy decision, but so if we have something here that is random, we need to have a prediction task for it. So if we add the claim status to this vector, we need to have a model for it. So we need to have a 3-task neural network. And it seems like for our data set, because there were a lot of claims reopening, and it didn't mean that a claim, if a claim is open, it didn't mean there was a payment. It seemed more useful to do this classification task on the prediction of the non-zero payment than the claim status. But one could decide to include the claim status and then add an additional task. That's possible. So here is the architecture of the LSTM. So in the first period, you see we input the claim context, which is the claim characteristics, and the dynamic information at period 1. So here I drop the index K for simplicity. This is passed through the LSTM module, which outputs a first hidden output. And this H1 is passed through a fully connected layer to get our prediction of Y hat, so the payment. And the same output is passed through a fully connected layer and a sigmoid to get a P hat, which is the probability of payment. And then this information flows through to the second module, and we have another prediction for period 3, and so on. So the claim context is C0. It comes from the information that is known on the claim, like the claimant age, the type of vehicle. So to put that in the claim context, we first did an embedding on all the categorical features. We scaled the quantitative features and then concatenated all of this. And to reduce dimension, we pass that through another fully connected layer to get a claim context of dimension C. So C here is a hyperparameter. So you've seen here that I have 2 targets at each period, but I have to optimize one loss function. So to combine the 2 loss functions, we use something that is called loss balancing. So here's the formula of the network Gaussian likelihood loss function. It's a combination of the regression loss and the classification error. And you see this alpha term here is really the loss balancing factor. So this hyperparameter could be set to alpha to 1 if the classification error and the regression loss lie on the same scale, which was really not our case. So to tune the hyperparameter alpha, we decided to choose it from a grid, and it's based on the performance and the validation set that is known at T star. And once alpha is chosen, then we can do the optimization problem that is optimizing for the network weights and the 2 variances that are in this formula here. So in the training, for a given period, the loss calculation involves only observations with non-missing targets. So everything that happens after evaluation date, we do not know what happens, so we cannot evaluate if our prediction is good. So those observations are not taken into account into the training. But as there are fewer and fewer observations when moving forward in the development period, we weight the sum by the number of available observations. So that's the formulas are available in the paper if you want to have a look. So for classification, we use binary cross entropy, and for regression, there are many options. We decided to use squared error loss as we allow for recoveries. So we needed something that could account for the negatives, but if you have only positive, you could use gamma deviance, for example. So as I said before, we need to be able to predict for the future periods, even if the inputs are missing. So when the input is missing, you cannot know what's the Y star and the I in the set B. So we use the prediction of the previous period as the input of the next period when it's missing. We actually also did that even sometimes when the input was not missing. This is inspired by the teacher forcing method in the LSTM training. So what it does is says like, if you always predict something and then later on you pass the truth, then the network doesn't know how to correct from its past mistake. So by giving with so with a probability that is increasing over epochs, we randomly choose whether to replace the observed with the predicted from the previous period, which allows the network to learn how to correct from its mistake and to have accurate predictions in the future period, even if there was a problem in the first period. So this replacement process was done either for the missing inputs or to improve the training. And we found that it was better to use the prediction because here p hat is a probability, whereas I was a 0, 1. So at first we thought maybe we need to simulate something to have a 0, 1 input, but it seemed like the prediction was better. So it gives a better training. Okay, so let me show you 2 examples. So first, the simulated data. So we used the simulation machine of Professor Wüthrich. Thanks to him and his co-author, we can use this simulated data. So it was good for us to have simulated data because now we can share these results and the code that goes with it. Whereas on the company data, we cannot do that. And it's quite a realistic data set because there are negative payments and reopenings, less than in the real data set, but still there are some. And there were settlement at 0. The drawback here is that there are few covariates, and the yearly development means that it's aggregated into years, so it's really not so granular. And we only have n equals 12. So because we have few covariates, it's expected that the granular framework will not outperform the traditional chain ladder framework too much because we don't have so much more information in this granular context. But it's still good to see the illustration. So to show the results, I will present the ratios of the aggregate reserves, either on the validation or the testing dataset. So it's always on payments after the evaluation date, so they have not been seen in the training and validation. And it's the ratio of the predicted reserve over the observed reserve that was actually happened in the simulated data, that was actually simulated, that should say. So here you can see that our model performs similarly as chain ladder, a little less good because here a ratio of 1 would be perfect prediction on the aggregate. So it's not so good, but it's not so worst as well. But with the LSTM model, we have more information because we have a prediction for each claim. And so here you can see, so the predicted probabilities are presented. So it's the box plots, it's the distribution of the predicted probabilities. In orange, it's the validation set, and in blue, it's the test set. And you see, if the truth was 0, we really predicted probabilities that are closer to 0 than when the truth was 1. And you see the performance improves with the development period. So at development period 5, 75% of the predicted probabilities at 0 here when we have an actual that is 0, and almost none were predicted at 0 when the actual was 1. So you see that our network captures well the behavior of the I indicator. So that's quite similar on the ROC curve. And for the payment, so the other task of the network is to predict the non-zero payment. So here you can see the predicted non-zero payment versus the actual non-zero payment for a few development periods. And so the association between the two seems pretty good. Of course, there are some errors, but it's the expectation. So we expect to have some random variation around the mean. In the real data, it was really interesting. So we had body injury claims with accident rate between 2006 and 2010. 53,000 claimants, and we had monthly development periods, so a little more granular. And the ultimate is 45 months. We had 16 static features, if the information on the claim or on the claimant or the vehicle. And we had 4 features that were dynamic, so that could change over time, the number of injuries, the degree of injury, etc. So for those, what we did, it's not perfect, but we used the actual observed dynamic covariate in the periods that were observed. And once we attain the evaluation date, we keep the last observed value, because we didn't want to add too many tasks to the network. And before doing the analysis, we treated the missing covariate with imputation with the R package mice. So the LSTM network worked well. So if you can see here, the ratios of aggregate reserve, so the same ratios that I talked to you about earlier. On the LSTM, we have very close to 1, whereas the chain ladder overstates the actual reserve, both on the validation and the testing data set. But what I'm not saying here is because we work on censored payments, because we had extreme payments in this data set. And so we used the LSTM to predict on the bulk of the payment, and in the tail, we adjust the payment for the extremes. And that's what I will discuss just after. So those are the results for the LSTM. And you can also see the predicted payment in function of the observed non-zero payment censored. So you can see maybe some of the values are censored at 32,000. So that's what we input to the LSTM network. So here there are more variation than in the simulated data, of course, but we still see a positive association. And with the other task, the task that is for the predicted probability of non-zero payment, the results were similar as in the simulated data set. So for the extremes, I'm a statistician, so I really thought we should do something about the extremes, and we used extreme value theory. So I'm sure you know, but if you don't, let me introduce the Pickens-Balkema-Dehaene theorem. It states that for a very large class of distribution F, we can use this excess function. We can look at this excess function, which is defined as the probability of x minus u being smaller than or equal to y, given that x is greater than u. So it's really the distribution over u. This distribution converges to the GPD distribution, the generalized Pareto distribution that is defined here, when the threshold u tends to the upper limits of the distribution. So when u tends to infinity, the distribution of the excess over u will converge to a GPD distribution, which means that for a threshold u sufficiently large, I can use the GPD, and it's going to be a good approximation of the distribution in the table. So what we did, we used the LSTM to predict below a threshold u, which we set with extreme value theory, and we did the diagnostic tools. We set it at 32,000, as I said before. And after we need a probability of being greater than that threshold, that's going to be another model. And then over the threshold, we'll use the prediction of the GPD, which will be the mean of the excess distribution that will be fit. So for the probability of exceedance, the probability of being greater than a threshold u, we use the Bernoulli GLM with development period and number of previous periods without payment as the covariates. So you can see here proportionate probabilities. And so there's a higher probability of exceeding in the late development months, especially if you have a lot of payment previous periods with payments. So in theory, it's really nice because we can adjust the network prediction for large claims so the expectation of Y would be the probability that I is 1. So the probability that there is a non-zero payment times the expectation of a non-zero payment. So this part I will break down. And this first part, it's our predicted probability from the LSTM at step J. This part I will break down into 2 parts. So it's the probability that the payment is greater than the threshold U, which will be my Bernoulli GLM probability. And this is the expectation of the excess over U with the GPD. And the second part is a probability of being smaller than the threshold, so 1 minus my predicted probability from the GLM. And this part is my LSTM prediction for the censored payments. So you can see here the formula for our adjusted network prediction. So it's really nice in theory, but when we implemented it, overstatement of the reserve, like gross overstatement. So it didn't work. So we decided to find a solution and apply the adjustment only for selected observations that had a great probability of being large, not to impact too much the payments that were small. So for the training data set, we analyzed the distribution of the prediction Y hat of large censored payment Y, and we chose the threshold Xi, I guess, Chi, whatever. And the prediction is set to the unmodified prediction if we have a small predicted payment in the LSTM, and we use the large formula from the previous slide if we have a bigger prediction. So we only adjust the claims that have a higher probability of being large. And this worked quite well. Here you can see the summary statistics of LSTM prediction. When you have large payment, it's around 3,000. So between 1,000 and 2,000 it seems like good candidate for our threshold to modify the prediction. So in this table, you have the ratios of aggregate predicted reserve over observed aggregate reserve. And so here on uncensored payment. So what I showed you earlier were only for the censored part. So now here, this is on the entire payments, the entire data set. So the chain ladder does not perform really well on our data set. It was overstating the reserves. And this case is when we adjust all the claims for large claims, all the payments, I'm sorry, for large claims. So this, when I told you it was a gross overstatement, you can believe me. This case, the case infinity, is when you adjust none of them for the large claims. And here we understate the reserves. And we found that the case where the threshold is set as 2,500, we have very good performance on the training, validation, and testing data set. So this threshold can be set based on the training data set, for example. And it works well on the testing set as well. So in conclusion, our model is adaptable to the structure of any claim data set with detailed development. Our approach treats large payments, and we propose an estimation and validation methodology that are based only on information prior to valuation date. We showed that the method works relatively well on simulated and well on real insurance data set. And we could add more tasks to the network to model dynamic covariates if required. The major drawback of this method is that we do not have a measure of uncertainty or a predictive distribution. So it's really a point estimation. So that's really something that needs to be improved, and it's a step for future work. And so this research was supported by a Canadian insurance company, the Big Data Research Center, and UNSERC. and I'm happy to answer questions.